Hey, eighth grade. Sorry that my face is a little dark, but this is kind of where I gotta hide in the morning when everyone's asleep to do this. But otherwise, main point of this video today is to go over or review for the volcano quiz, essentially. Look at some of the assignments that we did, the lab, and point out a few things from the notes that aren't on the lab that are important for the quiz today. But the other thing I want to briefly mention is the next chunk of notes on the rock cycle we're going to do as a Zoom meeting, and that is on May 6th, which should be Wednesday at 11 a.m. So the notes for that day won't be up like they have been in the past because we'll do a live session, see how it goes. If you have questions, you can ask about them. Show you some different rocks that day. I don't know. We'll see how it goes. So hope to see you there. Otherwise, let's take a look at the viscosity of lava lab. So there were a few questions on the first page, which I actually didn't have you post because I didn't see them right away. But whatever, there's only 3 of them. What is lava? I don't know if we actually talked about that in the notes. Should add that if we didn't. Anyway, lava is essentially magma that has come to the surface. So if it's below ground, it's magma. If it's above ground, it's lava. And then which flows faster, a high viscosity liquid or a low viscosity? So this whole viscosity thing is a pretty important concept for volcanoes. Viscosity means the thickness of a liquid, how easily it flows. So a low viscosity liquid will flow faster. Water is lower viscosity than corn syrup, for instance. You can dump water out instantly when you tip a cup over, where if you tip a cup of corn syrup out, it takes quite a bit for that to flow. So extrusive igneous rocks are named based on the composition of the lava that cooled to form them. Huh, you probably had to Google that one. Name 3 fine-grained extrusive igneous rocks. So basalt, andesite, rhyolite. Pretty sure you could have had obsidian in there, or some of the volcanic rocks, the volcano rocks that have like holes in them that float, like pumice or things like that. Okay, so then the rest were instructions. Now, we have kind of some rankings or orders here for the first couple. Basaltic lava is the lowest viscosity, andesite or andesitic is intermediate, and rhyolitic is high. Now, the reason why they're low, medium, or high is because basaltic has the lowest amount of silica, which was represented by the salt in our lab. So we put the least amount of salt/silica in our magma, and it was basaltic. If we put the most in it, it would be rhyolitic, and it would be the highest viscosity. It's the thickest, the slowest to move. And then how does increase in silica content affect the viscosity of lava? So small amount, small viscosity, high amount, high viscosity. So low viscosity lava viscosity increases with increasing silica. So whenever you do a trend like this, or how does one thing affect another, you have to describe both things. So if you just said lava viscosity is affected by increasing silica, that doesn't tell me anything. That could mean that the viscosity goes up, it could mean the viscosity goes down. So you have to describe what happens to the viscosity and the silica. So if I do this to the silica, this happens to the lava. Could almost word it like a hypothesis, I guess, something you could test. Then background, except that just freaked out. Okay, the background. Molten magma beneath the surface of the Earth contains dissolved gases. When the molten rock reaches the surface, gases attempt to escape into the atmosphere. When gases cannot escape easily, they will accumulate under pressure and eventually escape explosively. Evaluate how easily gases escape from each type of lava by attempting to blow bubbles in the mixture using straws. Okay, so this is the whole concept here is any magma or lava has gases in it, whether that's steam like water or CO2 or nitrogen dioxide. There's a lot of different gases that can be in it. And those gases are the things that are going to be held under pressure. And if you've done anything with like compressed air, whether it's in an air compressor cylinder in like a shop or those little spray cans to clean off your keyboard, anything like that, the gas is trapped inside of a place where it can't go anywhere. And as soon as it gets to the surface and it can go somewhere, it's going to try to escape and it's going to expand. So the easier it can do that without any resistance is a kind of like basaltic lava. It can flow easily and it lets gases escape, which makes the volcanic eruptions pretty mild. They'll erupt, but they don't really explode. The rhyolitic lava was the most difficult. It was the highest viscosity. It didn't flow well, and it traps gases because of that. Then the rhyolitic lava will be the most explosive eruption because of the fact that it traps a lot of gases and it kind of contains them. And since the lava has a lot of force that it kind of keeps in, when it finally does escape, it's going to be this big eruption. And then which type of lava will result in the least explosive, which is basaltic. Gases don't get trapped easily, they don't accumulate, is another word they're using here, which means build up. They escape quickly instead of having a bunch of gas accumulate and build up pressure like the rhyolitic would. And then clean the cup. Okay. And that leads us to something that's probably pretty similar to our notes. So, some of the stuff that we already went over in this um, lab itself is basaltic, is low silica, which means low viscosity. It flows pretty easily, relatively. Um, and because it flows easily, it doesn't trap gases, so there's not that many. The eruption they described as quiet. You could say mild, or I don't know, they form lava flows instead of erupting and exploding. And this is where you might have needed to Google or look at your notes, is Shield Volcano. And this is like Hawaii and lava. The big thing with Shield Volcano is the sides are very gradually sloping, and it makes these really big, wide volcanoes. So the Hawaiian Islands are a really good example of a shield volcano. Rhyolitic, we have the high, everything is high silica, high viscosity, high gas content, which means that they are very explosive. This is a cinder cone. So the big thing with the cinder cone is it's made up of a lot of volcanic ash and rocks. So I guess that's why there's a bunch of dots here. Very steep sides. The caldera, the crater, is very wide and broad. It's the best way, actually, this is a really good example. Best way to describe the way that a cinder cone looks is think of an ant hill that you might find on the sidewalk, except supersize it. It's made up of loose particles like dirt or tiny chunks of rock, and it's got this crater in the top that's just kind of caving in because stuff was moved out of the way because of the explosive eruption. It's not solid by any stretch of the imagination. It's kind of a big, giant anthill. Right. Then we have andesitic, which is the in-betweener. So all of them are medium. and it alternates between the eruptions, or you could have said moderate or medium eruptions. It's not. Sometimes they're the lava flows like the basaltic, sometimes they're explosive like the rhyolitic. And because of that, they make a composite volcano, kind of a combo of the two. So you're going to have a traditional, what you think of when you think of a volcano looking drawing here. It's very tall mountain, very steep sides, kind of triangular. It has a crater on the top, caldera is the fancy word for it. But then if you dig into it, you're going to find alternating layers. That's the big thing with the composite. You might have a lava layer where it's igneous rock and it's solid, followed by a layer of ash and tephra, followed by another lava layer, so on and so forth. Okay. So if I just briefly look at the notes here. Okay, another one to know is where the volcanoes happen. So plate boundaries is some of them. Know why it melts and whatnot. So when the plate goes under, it gets hot, but the water helps it melt, which makes magma rise. Volcanoes do happen in other places that aren't on plate boundaries, but it's usually due to a hot spot, which is a plume of magma that kind of forms in the mantle or the asthenosphere. It's hotter for some reason. They're not really sure why. This goes over all the stuff that we did in the lab, so no need to point out anything extra there. That's weird. I don't have anything in here that says magma is what you call stuff below ground, and lava is what you call it above ground. Closest I get here is this. It's in the ground, it's magma. It's above ground, it's lava. There's literally no other difference. Okay, and that's all. Okay, that's the only other thing. Hmm. Okay, I guess that's where I did it. I did it in the earthquake spot. Hmm. Might take that question off or something, but who knows? We've got earthquakes was another thing that we were going to do, but I needed compasses for it and didn't know if there was any way to really get those to you because not many of you probably have a circle drawing compass laying around your house. But volcanoes can cause smaller earthquakes, and that actually causes or helps us know when a volcano might erupt. So just because the magma pushes on rocks and it shifts things around, and that's all an earthquake is rocks sliding past each other. They aren't known for creating big earthquakes, but they do create some, and they're big enough to detect with a seismometer. So just wanted to point that out too, that volcanoes can cause earthquakes and can be detected, sort of, or predicted, sort of, with the fact that earthquakes are kind of increasing in frequency, how many there are. Okay, with that, good luck on the quiz and see you around.